Okay. So for today, what we will do, we will start from our Friday's class where we discussed the volumetric flow rate and the mass flow rate and the average velocities and everything. And from there, we will try to come up with the expression for the conservation of mass. And then if we have some time, we will do some mathematical problems. If we don't have any time, we will not do that. I don't think we will get time because for section 1, I couldn't get any time for the mathematical problem. But that's what we will do that on the next class. So you will not have any new class lecture copy for the Wednesday. The one I just gave you, that is for today and for Wednesday class. Okay, so make sure you bring that for Wednesday class. Okay, let's start this one. The volumetric flow rate, we started that. We said that Q equals to AV, or which was the volume over time, right? That's what we said that. And after that, thank you very much. After that, we discussed what is that V. So what is the characteristics of that V? This V can be anything, or that V should be what? Perpendicular to the cross-sectional area or cross-sectional surface. Yes. And that V is actually the average velocity. So we don't have to measure the velocity at this point, this point, this point, this point, this point individually. Rather, we will use the average velocity, that is the V. Yes, yes. Or you can just write down a few things there. Yeah, that is a part of the review. Okay, so then the average velocity, instead of measuring individual velocity at any point, you can just write down that V equals to Q over A. That means if you know the volumetric flow rate and if you know the cross-sectional area here, okay, this is A and this is Q, that will give you the average velocity, right? After that, we discussed the mass flow rate, which is M dot, that means mass over time. And since mass and volume has a special relationship, we can establish that relationship by the density. We can do the same here also. So rho times A times V, that means. Okay. So that's where we have stopped. And we also discussed something about the control volume, like we use this class as a control volume, which is fixed in the volume, right? I can't change the volume of this class. Like obviously I can make a wall or something that will reduce the volume, but I don't need to do that. It's like without doing anything, I can't change the volume of this class. So the volume of this class, the control volume, is kind of fixed, right? But we can have some other types of control volume also. Just think about this one, a rocket or something. And if we are studying with a small part of that rocket, maybe this one, just this small part, that part is it's fixed, but at the same time, it's not static. It is moving with the rocket with a certain velocity, right? And think about this one, that inflated wall or something. The more air you are like inserting in this tube, the more the volume it is getting, right? That means it's just the expanding. Just think about a balloon. The more you insert the air inside that balloon, it will change the shape, right? That means the control volume can be fixed, it can be moving, It can be expanding, shrinking, something like that. So let's write down the definition of control volume. What will be that? So control volume should be a volume fixed or moving or changing the volume. Changing with a constant velocity. Okay, so that is the control volume, and we can have fixed control volume, moving control volume, and the changing control volume. Now, the next topic with the control volume is control surface. Okay. So just from the name, can you tell me what is the control surface actually? The surface or surfaces of the control volume, right? Now, if I just consider this one here, and the flow is going from this side to this side, how many surfaces we have here? The first one is this one, right? One, this side. The next one is this one. And the last one is like this surrounding surface. So we have three surfaces here, and the definition should be surfaces of control volume is called the control surfaces. Okay. Now for this one, the control surfaces, let's use another example in the next slide, which you have a picture on your copy, I guess. Are you done with this one, everyone? Now here, so this is a setup with flow is coming inside from this one, and flow is going out from outlet B and outlet C. And if you consider these as a like circular pipe or something like that, this one, okay. Now, can you tell me how many surfaces we have here? This one is one, right? Okay, one, this one is two, this one is three, and this one we have four. So we have four control surfaces here. We will try to classify these surfaces into two parts, okay? So control surfaces, the first one is open, second one is closed. I'm saying open control surfaces because through those surfaces you can have some flows. So from this picture you can see 1, 2, 3, they have some sort of flows inside those, like perpendicular to that surface, right? But for surface 4, it's just the surrounding one. Are you seeing any flow going in or going outside from that surface, just for surface number 4? There is nothing, right, for surface number 4. So open surface is, it's like surface number 1, 2, 3, and the closed surface is 4. That means open surface through which fluid can flow. That is the open control surface. And the closed surface is fluid can't flow through these surfaces. I mean, there can be flow along that surfaces, but there is no flow through that surface. Okay, that should be the closed surface. Okay, and all the time from now on, we will always deal with open control surfaces. Even if I don't mention that it's open control surfaces, whenever I say control surface, that should be the open control surface. Okay. Okay. Now, this one again, the same picture. We know this is number 1, this is number 2, this is number 3. So for any open control surfaces, there has to be 3 components. The first one is cross-sectional area. Like if I draw the, you know what is the control surface, the cross-sectional area, like this one. Okay, or this one here. So you will need cross-sectional area. You need a velocity. Now there is a condition. The velocity should be what? Perpendicular to the area for getting the Q. But you can't always make sure that the velocity will be perpendicular. If it's not perpendicular, we need to take a component of that to make the perpendicular. But at this point, I will just write down velocity. One more thing, we need to know the direction of velocity. How many surfaces we have here? Again, the control surfaces in this picture. How many open surfaces we have here? 3. Okay. For number 2 and number 3, flow is going inside or outside? Outgoing. For surface A, flow is going inside or outside? So that means we can have incoming flow at the same time we can have outgoing flow. So we need to make sure we know the direction of the velocity also, right? Because velocity is a vector quantity. And that's why we need this normal unit vector. Normal means it's perpendicular. Unit means what? Just 1. Whenever you hear the word unit, that means it's 1. So the magnitude of this vector is 1. This one is outward. And this is a directional vector. So these are few properties of that unit vector. It will be always 1. It will act outward, and it will give you some sort of direction of the velocity. So now I will write down the equation a little bit differently here. Instead of V, I will just add the direction also. Okay. Do you remember the dot product and the scalar product? Little bit maybe. Or do you remember the name? Okay, that will work. So for the cross product, it's just you need to know the angle between the quantity, right? So I will write down this way: A, V, N cosine theta, and theta is here. Are you seeing this picture? The V is going this way, and the N should be always perpendicular or perpendicular to the surface actually. And the theta is in between that V and N. So whatever the theta is, we need to consider in that way. Now, just without checking the calculator, what is the value of cosine 0 and cosine 90? Okay, so we will need that value. Just remember that. But that's how we can make sure that we are making sure the velocity has some, like we are taking care of the direction of the velocity also. Okay. Okay. Now, you can remember we said that there are two approaches for the fluid flow. One is I will stop you in every class from here. That was the Lagrangian one, right? And then another one is I will be here. You will come to this class and I will just monitor what you are doing inside this class. I don't care what you are doing outside of this class, right? So that was the Eulerian approach. Now, all the conservation principle like mass conservation, energy conservation, momentum conservations, those were developed based on Lagrangian one, but we want to do all the calculation based on Eulerian approach, like within the control volume approach. So we need to have something which can connect these two. And that connection is actually the Reynolds transport theorem. So someone named Osborne Reynolds, he actually introduced this one, and you will see we will use this Reynolds thing in other part of this fluid flow also, but not here. So, okay, so we need to connect these two approaches by Reynolds transport theorem. Before I write down any mathematical expression, let's discuss the concept of this Reynolds transport theorem. Okay. Now, what I will do, I will use the same same example of this room. Okay, with inflow and outflow, and all of you will act like a fluid particle. Okay, so we have 15 people, so 15 fluid particles. Okay, so this is the classroom we are having. So this is our control volume. Okay, now for control volume, all these wall, you can't go through these wall, right? Unless you have some superpower or something. You can't go through these walls. You have to come through that door, right? Okay, so that is the door, and that is just open control surface. We have door, and how many windows we have here? Well, okay. Door is just one. Okay, we already discussed that door. Or how about we just say we have 4 windows, because like we will just consider these as just one outgoing, like opening. Okay, so we have windows, door 1, windows 4. Now, this morning at 8:50, 15 of you came through that door, right? So that is the incoming flow. Through the surface, right? Now, at 9:20, 5 of you are just so pissed off. Okay, it's right after FTX weekend. I can't do this anymore. Again, I'll jump through the window. So 4 of you would jump through these 4 windows. So that means that is the outgoing flows, right? Flow through the surface. Okay, now, is there anyone who is sleeping or doing something else? Ah, too bad. Okay, so I needed something. So within this control volume, suppose someone is doing something. I can't see your screen, so I don't know. So within the control volume, maybe someone is sleeping or doing something else other than the class, like the fluid class or something. Now, if I want to write down, or if I want to do the calculation of number of attentive students for the whole class period, like for the whole 50 minutes, like the 50 minutes, obviously I need to consider the incoming flow, outgoing flow, and though I have like you came 15, 5, 4 jumps, so we have 11, but within that 11, I'm sure I'm not having 11 students for the whole time. Someone is sleeping or someone is doing something. That means I'm not having 11 students, the attentive students all the time, right? So how many factors do we have? We have something for incoming. So I have something for the incoming cadets minus outgoing cadets, and I'm just adding a plus sign, but it will depend on the situation. So something cadets inside the classroom who are sleeping or something. You can see the line here. Okay. I will just write down who is not attentive. Right? So the main thing I want to convey to you, that the thing is, just like this attentive student, if I want to do something about the fluid flow, I need to consider what is coming in, what is going out, and what is happening inside that pipe or the control volume. Okay, so we have in total 2 components. One is through control surface, one is through control volume. Okay, so now I can write down the mathematical expression. We will do that if you're done with this slide. Okay, all of you are done with this one. Okay, good. So what we will do, just write down here that, or I should write down here. Okay, you have this space, don't write down anything at the very end, just write down this one. So N is some properties of the fluid, and it will be something EA. Okay, CV means control volume. Okay, and CS means what? Control surfaces, and obviously the open control surfaces. We are not doing anything with. Okay, so this part is students within the class not attentive, and this part is incoming and outgoing students, and in total that is number of attentive students. Okay. Now this n, that is called the extensive property, and this eta, that is called intensive property. Can anyone read what is the extensive property? What is the definition of extensive property? Okay, that means any property which is related to mass. Can you give me one example of in extensive property, anything? What is the very close thing related to mass? Say it again. Okay, yeah, density m over volume. Okay, that can be one property. Okay, anything? Yes. Okay, weight, which is m times gravity. Then it can be momentum, right? So anything related to mass, that will be the extensive property. And what is the intensive property? Can you read the definition of intensive property? Any property which is independent of mass. So what can be an example of intensive property which is not related to mass? Viscosity. Viscosity is related to density, so which is actually kind of related to mass. One common thing can be temperature. What did you say? Say it again. State of matter. That's what you said. That is again related to mass. What we can say, but what you said, state of matter, we can connect that if we just say length or volume of or area of the fluid, right? Length, area, volume, like anything which is not related to mass, that can be the intensive property. And that's what they, based on these, they wrote this equation. Now, is there any way you can change or you can convert the extensive property to the intensive property? Yes. What is the way? Just think about these weight, m times gravity. How can you remove m from this equation? Divide by m. Yeah, that is the easiest thing you can do. So if I just write down, are you done with this slide, everyone? I know I wrote too many things on this slide. Yes. dn over dt, that one. This one, d over d. Oh, that's just the eta. This one, the intensive property here. Okay, for few classes you will be a little bit confused with this eta and the unit vector n, but I'm just using this eta because that's what they used in your textbook. So if you want to go through your textbook, that's what you will see. But I don't like that personally, to use the eta for the intensive property. You can use anything else, that doesn't matter. Okay, so are we good up to this point? Okay, so this is the equation again. And what you can do, intensive property and not n, the eta equals to extensive property over M. That means eta equals to N over M. Okay. And let's write down what are the other parameter mean here. That is V. Okay. So tell me, what is N again in this equation? Oh, this capital N, this one. Extensive property, right? What is T? What is T? Time, yes. What is eta? Intensive property. What is rho? Density, mass times volume. What is V? This one is the volume, yes. What is that V? The V vector, there should be, yeah, so this part is actually, it should be V times N. So this one is, and the N is unit vector, right? And A is what? The very last one? Cross-sectional area. Okay, so now we know every term of that. And based on this theorem or this expression, we will come up with the expression for mass conservation, energy conservation, and the moment conservation. Okay, so for today's class and for next day's class, we will work with the mass conservation. Once we are done with mass conservation, we will work with energy and then the momentum. But these will be the basic equation we'll start with. Okay, now when we say mass conservation, I know you know what is mass conservation. So what is that actually, the mass conservation? What is the general statement of mass conservation? Mass should be conserved, right? What does that mean? You can't create or destroy any object like the matter's mass, right? Unless there is any nuclear process or something. In that case, you can change that. Like all the like atomic bomb or something like that. Obviously, there is some sort of reaction where one particle can be increased into multiple particles. Okay, but we are not discussing that part here because that is kind of like a special case. We will just do the normal one, which is within a region, apart from any nuclear process, matter can neither be created nor destroyed, right? Now, this is a very simple statement, and we are working with a huge complex equation here, right? That's because that equation actually considers every possible scenarios we can have. But as I said, we don't need to use all the scenarios all the time. So what we will do, at first, we will write down the general expression, and then sequentially, we will reduce one term, and then you will see the final version is not that much complicated. Okay, so let's work on that. For mass conservation, the extensive property is mass. Okay. And the intensive property is mass over mass. That means M over M equals to 1. Okay. So now what you will do, you will insert these two values instead of N and instead of eta in the equation. And let's see what we can get from here. Okay. So I will just write down the initial equation, dN over dt. CV plus CV means what? Control surfaces, right? Sorry, control volume, and CS is the control surfaces. Yeah. Okay. So for mass conservation, this one is M, this one is 1, this one is 1. So the final version is dm over dt CV rho. I'm sorry, that should be for eta, not for the row. So for this one, it should be 1. Okay. So rho p times n times e. Okay. So obviously, this is not simple as when we say mass can be created or destroyed. We have huge integral term here. So what we will do, we will try to simplify this expression for our regular use. Okay. The very first simplification will be mass should be constant, right? That's what we said. Mass should be constant over time. That means there is no change of mass over time. dm over dt will be 0, right? So this whole term is, you can consider 0. 0 equals to d over dt CV So now we got rid of one term actually. We need to work on some other simplification also. We'll do that. And we will do that under special case. Okay. And the name of this equation at this point, it's called continuity equation. We have 10 minutes. I think I can finish that. If I can't, that is okay also. Okay, everyone's done up to this point? The back, are you done? Okay, so the special cases, what we will do, the very first special case is steady flow. Can anyone tell me what was the definition of steady flow? That is kind of true, but it is related to time, right? Like the velocity or fluid properties will not be changed over time, right? So steady flow is what? Fluid properties don't change over time. That means if I write down that equation again, this term, this whole term is 0 because it's d over dt, and that's not possible for the steady flow, right? So the final expression, what did we get? Rho mass conservation for steady flow. And in this course, I said that we will not do anything with unsteady. That means we are actually using these equation for all the time, okay? Because we are not doing anything with the unsteady for this course. So make sure you know this one. And from the huge complex equation, we came up with these expressions. Still, it's a little bit complicated, but it's not complicated as we started, right? Okay, so we need to do one more simplification. We will do that. I need to go to the next slide. If you're done, we can move to the next one. Okay. Okay. So for this one, for steady flow, we got that CS rho V times N times dA equals to 0. Now for this case, how many control surfaces we have? 1, 2, and 3, right? Or actually open surface, like control open surface, right? And on this one, for 1, it's incoming flow, right? And for 2 and 3, those are what? Outgoing, okay? So what I will do, I will just remove the integration. Instead of integration, I'll just write down the summation. And instead of dA, since I already did the sum, I will use A. Okay. Now from the control surface, we can see we have some inlet, we have some outlet. What I will write down, instead of control surface, I will write down inlet plus, I'll write down outlet. Okay. I will do one more line, inlet, and I will remove the dot product sign. So I will do what? Rho V n cosine theta A plus outlet rho V n cosine theta A equals to 0. Okay. Why did I write down V n cosine theta? This is the dot product, right? Are you done with this slide? Okay, I will wait. This one? We need to write down one more line, but I will move to the next slide because I need to draw something. You're out of space on your copy.
I circled the last.
Oh, okay. We will do that. You're done? Okay. So here, if I just move this part, this one was 1. Which one is? Oh, this one is 3. This one is 2. Okay. So for 1, what is the direction of V? Right, like going. Okay. And what is the direction of N? N is always outward. So N is, what is the direction of N? Okay. And what is the angle between these? Okay. And for 2 and 3, the direction of V is this. What is the direction of N? Again, the same. And the angle between them is what? I should write down this way. Is there any angle between V and N this time? So this is 0 degree. Okay. So that will help me with the previous equation, what we have wrote here. I need to check that Vn cos theta A. Okay. So for inlet, this one is inlet, this one is outlet. So you told me that for inlet, the angle is what? 180? Plus rho V n cosine 0 A equals to 0. What is the value for cosine 180 degree? -1. And what is the value for cosine 0? So can I write down this way? -1 rho V A well, +1 rho V A equals to 0. Can I write down that way? So the very final one will be, since it's negative, summation of outlet rho V A inlet rho V A equals to 0. Yes, for steady flow. Okay, so that is the final expression for mass flow rate for steady flow. We have one special case, but I don't think we have time. But what I will write down here, can you check the very first part of this lecture and tell me rho VA means what? What is the, is there any specific term we can use for rho VA? I'm just writing down the same line here, rho VA outlet minus rho VA. Okay, tell me, what is the name of rho VA? M dot. If I go at the very first slide here, rho AV equals to M dot, right? That means M dot summation of M dot outlet inlet equals to 0. That simply means inflow equals to outflow, right? Thank you, class, for today's lesson. And we will start from this point. We need to do one more simplification, and then we can start working on our class example 15. Make sure you bring your class example 15 for next class, okay? I will see you on Wednesday. You all have a nice day.